Welcome everyone, welcome. We're here again to another episode of the Engineering Bard Show. Okay. Wait till this guy goes. This guy is an amazing guitarist, yeah. Alright, we got a great show coming out tonight. We got talk about the car a bit more. We're going to talk about the right-hand rule. We're going to talk about the chips that I use. We're going to talk about the capacitor, all that, so to make this design possible. So I hope you guys enjoy my show. Put a like, put a thumbs up, and please subscribe to the Engineering Bard Show. I'd like to thank you. Thank you, everybody. I hope you guys enjoy that. A video there, a little bit of an introduction. Now we're going to do the right-hand rule one more time. Some of you guys didn't see the little DC motor video that I put out. So here we go. My thumb is the conductor going up from the bottom of my hand to the thumb. So just imagine a wire, but imagine the motor is my thumb, okay? That spinny thing. That spinny thing. That's my thumb, okay? Spinny thing. See, it spins. Now, I'm aiming towards the camera, and I curl my fingers, and the rotation of the fingers starts from the knuckle to inside. So I got a big old thumbs up. We're going counterclockwise. Counterclockwise, okay? Thumbs up. Now that is when the going through the motor. Now if I reverse the leads, I go down and now I curl my fingers this way. It's going clockwise. Counterclockwise, clockwise. Now in there is the force. I do believe the force is orthogonal to it. It's either this way or that way. There's the B field force. Point out, point towards you, and then right here, the B field is going away from you when I put the thumbs up. Okay, now we're going to go to the lab part, and we're going to see this so-called theory into action with my battery over here. If I can move this camera without, this is a stubborn little camera. Okay, here we go. So the wheel is spinning counterclockwise. Remember the thumb on the last video, thumb's going down, okay? Just to simply put. All right. And, okay. So, there's. Now, I'm going to reverse the leads on the battery, and you'll see it go the other way. So we're going to go here, and we're going to go here. Now it's going forward. And watch the power. See the power supply current. As I turn on the voltage, it gets faster. But look at the current. It's kind of stressing out the power supply. It's going, what are you doing? It's just a wire shorting me out. Oh no. You see how it's going up? Sometimes you might need countermeasures. So hope you guys enjoy that, and let's go off to the next section. This is the quadruple H drivers that I have. This is the chips that I use. This is the chips that I highly recommend that you guys use. And I'm going to try to get this. Oh boy. Hold on, guys. It's just okay. Trying to get this. So from here on out, this is going to be 5 minutes or less. Okay, so let's go through this chip 1 through 8, 9 through 16. I'm going to go pretty quick because I think I don't need to spend too much time on it. So 1 and 2 means enable. And to enable, it needs to be on. You're going to use your controller to enable that. Now, it requires if you look on the data sheet real quick, which is pretty important. It required the supply voltage is 4.5 to 7 volts max. Basically, it requires about at least 5 volts. Okay, so we're going to your controllers is 3.3 volts. Some are even less. We'll have to discuss how to solve that problem in future videos. Okay, so 1A and 1A is the forward enable, or it depends. It's going from north to south pole. Let's go ahead and do that. So 1A has to be on, 2A has to be off. That has to be off to work. That has to flow. You can't have it going. If 1A is on and 2A is on, nothing will work. Okay, the 1Y and the 2Y, that is where you hook up the DC motor, and the VCC1, that is the supply voltage. So remember that I showed you that on the last video on the car where I have it hooked up. I got my 12 volts hooked up to 16. No, excuse me, to 8. And yeah, VCC2. The 5 volts goes to the VCC1. Okay, VCC2. To kind of show you real quick, and yeah, goes to VCC1 36 volts. That's up to 36 volts and up to 36 volts. So 4.5 to 7 VCC. That's the supply voltage, 36 volts. And it can take quite a bit of current. I did see an amp. Now, this is the time delay when it changes back and forth. Yeah, it's not super fast, 800 nanoseconds, but that's less than a blink of an eye. Okay, and it's always good to kind of, check these things out. It's kind of like, oh, okay, it's kind of interesting, these little sheets. Each current can take about 600 milliamps. That's plenty of current. That's when it's drawing. That's when the motor is drawing. Anything after that, you might need a bigger. If it takes over like an amp, you might want to get a bigger, a more beefier chip, or get a. You'll have to do it by. You'll have to build it yourself. And I'll kind of show you how to do it on the board just to get a better idea on how it works. The 1Y, and those are where your motors go. 1Y, 2Y, 3Y, 4Y. That's for 2 motors. If you only have 1 motor, I'm jealous. All you need is just one side. Or if you only got 2 motors in the back, but the front just sort of is just a servo, hey, that's cool too. All you need is just one chip. The car I bought had. It had 4 motors, but it didn't have a nice servo in the forward. Okay, and there's the thermal protection. I guess the thermal protection, maybe when it catches on fire, I have no idea. Don't kind of believe that. Just kind of make sure everything is hooked up right, and don't pull too much current, okay? And all right, so let's go off to the next section. We're going to discuss the circuit right here. We're going to discuss the circuit. This is called an H bridge. I was trying to explain that on the last video there. So we're just looking at it. Called an H bridge because this is the original design when it first got implemented. It looks like an H. See, it's kind of like an H as in Harry. Okay, and this looks confusing at first. I had to think about this. These diodes right here are to protect it. So the diodes, are these diodes in forward bias or reverse bias? At first glance, I said, oh my gosh, how does the circuit work? It's in reverse bias. These diodes right here are only to protect the back EMF. Okay, so this right here is a MOSFET. Metal oxide, silicone, FET. Okay, and this So this looks kind of confusing, right? So let's go ahead and erase. So a MOSFET is a switch. A diode, this diode right here is basically an open. So current does not flow in this diode only when it's kind of like, it acts like a release valve. So it protects this right here. This right here is a switch. So go ahead, let's go ahead and erase this because it's a little confusing, right? So I know my audience is like, oh my gosh, what the hell? So when, okay, and then this PC, I think it was 0, okay? So when PC 0 is on, okay, I want PC 0 on, and if I have turned this into a switch, okay, that's now a closed switch. So current, okay, that's an open switch. Okay, so we're just going to turn that into a switch. Okay, so that's a switch. Okay, that's like, so current's going to flow from, or electrons will flow. Okay, let's do conventional. It will flow from here to here. So you got to make sure that PC0, PC2, whatever your port is to turn this on, has to be what? 5 volts, not 3.3 volts. Current will flow into this direction. So assuming that, so it's going to go forward. Okay, forward. Okay, it's going to go forward. That's the motor spinning. So it's spinning like, kind of like that, okay? Now that's PC0, PC2. So now that's a switch. It makes it look easier. Now let's go ahead and open this switch. Open that switch. Okay, open. And we're going to close this switch. And we're going to close this switch. Now current will flow through the motor, and now it's going the opposite direction. That opposite direction. So that right there, so that right there, you see how it was circuit form, but that's how you could turn. I put like 100 volts. Let's say you want a big motor, but you would need a big power MOSFET. They have those. I don't know where, but they're like, you know, they're for like big motors, or you could use a transistor, or you can even use a relay. Okay, you can even use a relay if you do it right. So one of those big power relays, you know, something like that. I mean, from a 12 volt to like a power relay, anything that works like a switch. All right, so let's go off to the next section, and we will talk about. We're going to talk about the limitations, or we'll talk about how to enable the embed, at least my embed, to make sure it works off of the battery. And then we're going to talk about how to convert voltages back and forth. I'll see you there, okay? Okay, so now we're going to talk about the power limitations of the microcontroller and other development boards. This doesn't limit to mine. It limits to almost any type of development board that requires some sort of digital processes, logical processes. Okay, so here's some of the questions that I was thinking, and I hope you guys think about this. Now, sometimes I know I attached everything correctly from the development board to the external IC. Why does my circuit not work? That is a very good question. Those are questions that you have to consider. Those are some troubleshooting questions. We'll get to that. That's in this section is also a troubleshooting question that will answer that even further. How do I convert my lower direct voltage to a higher direct voltage, or vice versa? And we'll talk about the limitations on that too. How it's hard to, you can do it it's easier to do it from AC, but let's talk about that a bit more. What is wrong with the voltage divider circuit? A lot, but we'll talk about, we'll go to the board on that. And what are some of the hacks to reliability to reduce noise coming from the battery and other external sources? We're going to talk about how this is a hack that I came up with. I did this in school. It's a very interesting hack that I did to solve a couple problems. So I got this picture. I was thinking about this. I was thinking about this. I was thinking about what is this relationship? So sometimes I watch these B grade films. I guess it wasn't B grade. I was actually A. It had this is Masta Blasta in the 1985 Mad Max Beyond Thunderdome, and it started with Mel Gibson. And this is one of the back then that was supposed to be like high tech. And there was this scene out there where Mel Gibson fights this guy, and this Master Blaster, he controls everything. He controls, the little colony, and he controls this big dude right there. Anyone gets out of line, this big dude gets out of line. Well, Master is this little dude that rides on a little chair, and he rides on the back of a Blaster. And Blaster's like this big guy, and he has like muscles everywhere, and he goes to fight with Mel Gibson. Of course, Mel Gibson kicks his ass, right? Good guys always kick ass. Bad guys can't even, if they shoot a good guy, they can't even hit a broadside of a barn. But it's an interesting relationship when it comes to electronics. Master is like your controller. Even though it says 3.3 volts and 5 volts, if you scoot it up, there is, as we showed that on earlier videos, has 3.3 volts. It has the voltage, but the question is, does it have the power? And as we know, power is, if you don't have the power, you're not your chips, your IC chips that controls it will ignore it. It'll be like 5 volts. You're just some you're just some small dude. Now, the Blaster is a battery. This is the battery that I have. This is a pretty burly battery. It has 506 milliamps. Blaster without Master is just a battery. It doesn't do anything. I mean, it powers anything it wants. But Master, in order for Master to be powerful to control the rest of the circuit, he needs the Blaster. And so this is sort of the relationship you need. So your Master, what I'm saying is, just because it has 5 volts here, 3.3 volts, don't use those. Those are not very powerful, especially when you get into smaller. Those are not very powerful. Those don't have a lot of current. So some of the other chips may ignore it. So you may need an external source to boost that power so it will engage. All right, we'll talk more about these concepts on the board. I'll see you there. Okay, so let's talk about we're going to talk about the components of what was going behind my head, and I hope this is sometimes you're thinking. So this is your controller right here. Say this is your embed. It's your embed, okay? It says 3.3 volts. It says 5 volts. I showed that on the last video there. We know that some of these ICs may require, let's say it requires a half a watt. 1/2 watt, okay, 1/2 watt. So V times I equals your power. Okay, so if your power is, okay, so if your V is 5, okay, 5 equals, and then you got your power 0.5, okay, 5 divided by 0.5 is, well, let's check that out. 5 divided by 0.5, well, that's going to be, I think that's going to be like 0.01, something like that. It could be 100. 5 divided by 5 divided by 0.5. They go over here. Okay, yeah, that's right. So it could be 100 milliamps, approximately. 100 milliamps. I kind of had to do some long division. 100 milliamps, approximately. Okay, because 5 divided by 5 is 1. You scoot it over. It's 0.1. This all has 10 milliamps. That's not going to work. That's not going to work. So on your data sheet, we'll say how much power it requires. It might not work. So you may be getting 5 volts, but then it's like, well, how come I'm getting 5 volts? It's probably because it's not meeting the power requirement. So you will need an external battery or, source. Master needs blaster. Okay. This is master external battery source. So my battery that I have this is sort of an interesting concept. I get that. I'm kind of like you guys. Like, well, there's all this stuff. Especially when it comes to current and you're reading the battery. It says 12 volts, 5 amps. Okay. And it's like 5 amps. That's going to blow up my circuit. Well, think of it as kind of like a bank. Think of it as kind of like a bank. This may require, I don't know. I'm going to do for math purposes. Maybe this requires 20 milliamps. Then you got, this is an IC. This require maybe 500 milliamps and all that. So that doesn't need, so that would be okay to, and this is connected, let's say. And that connected there, that's connected to ground, okay? Just for formality's sake, okay? That's connected, that's connected. Everything is connected. This is the basic circuit. Now, that's okay. So your battery is fine. The only time it's kind of now if you want your battery to design your battery, if you think that's an overkill, you want it smaller, you can do that. You could calculate how many wattages is coming, add it up, subtract your amperage, and then you say, okay, it should work. Where it gets kind of bad is where you have the batteries too small. However, if it draws too much current at a time, the smaller the battery, you also got to look for amp hours, so it might not last as long. So the lower the amp hours, the longer your car will work on a battery power. Now, that's great if it's battery power, and battery power is important, but you still haven't answered the question. Well, okay, so we have a battery, 12 volts. Okay, this is 12 volts. Why not use a voltage divider? Okay, so let's voltage divider right here. Okay, voltage divider right here. Okay, right here. Let's say you get a 10K right here, 10K right here, and now you come across right here and you get 6 volts. You get 6 volts. Okay, 6 volts that should do it, or whatever you want. 6 volts. You have to do the proportions correctly. The problem with that is this whole circuit loses current, and it creates. So here's the problem. It's simple, yay. Your pros is let's do like a con, is it's simple, it's cheap, It's cheap. It doesn't cost hardly anything. It's small. Less room, and a lot of places. A lot of even your school will probably do like, let's do a voltage divider. But here's the con: you lose current. You lose power. A lot of it. It makes noise sometimes. Okay, it makes noise, and that is bad, especially if you do an RF circuit. We haven't been doing RF circuits, but when we're doing logical circuits, a noisy circuit creates noise. It creates, loses power, creates noise. It costs a bit more, or you could create your own. I'm going to show you the basic concepts of it. And believe it or not, we've been kind of doing it all along. It uses PWM, pulse width modulation. But I'm not going to go into heavy detail because it's like, power electronics is like its own its own degree in itself. It's like everything else. So it loses power. Loses noise. It makes noise, and it creates heat. Creates heat, and heat, as you know, is very inefficient. I can't spell, but it's very inefficient. Okay. Very inefficient. Anytime there's heat, you're getting an inefficiency rate. That's why the automobile cars only has like a 20% efficiency rate because most of that is lost through the engine. The engine is incredibly hot. I don't know anything about Teslas. I heard that those guys are cool, so I don't know anything about that. They may use some of these concepts. I don't know, but they might. Okay, so all that stuff is bad. So to go from 12 volts. Oh man, these damn pens. 12 volts. 12 volts. And then you want to go to 3.3 and then another one to 5 volts. Is you use something called a buck converter. Buck converters are basically they use a circuit. I'm going to try to draw it the best I can I'm going to draw it the best I can as off of my memory there to kind of to sort of get an idea of how it works. So this gets a buck converter. So basically, and in a way, it works great. As 12 volts, 5 amps, as voltage goes down, as V goes down, your I goes up. So it's kind of like you even got more of a bank. So that's like, so you get 3.3 volts. You're not going to get more than that. You're not going to get more than that. But you're not going to get more than 5 amps. But you could get almost up to it. So it's not going to create more amperage, but it might though. Okay. So the basic circuit is, here's a battery right here. Okay. 12 volts. And then it goes, there's like a capacitor right here. And then there's this right here. Okay. Which is sort of like I think that's the gate. And then it goes down here. And there's like a diode right here. And there's like a capacitor right here. And this is the load. It looks something like this. But, oh wait, this is a coil, excuse me. Ha ha ha, sorry about that. There's a coil right here. Whoop. So we know, hope you guys watched it, but the coil, when it goes, there's like this PWM. It's it's switching on and off. It's a high power switching power supply. It's switching on and off. This coil is collapsing. This is switching. The current flows through the diode. It's not coming back. It stores it. So there's a magnetic field. It switches, one-way valve, and then it stores. And then it basically releases. So that's how it sort of works. So the efficiency rating is almost like a 98% to almost, very, very high percentage. There's no resistors to collect all that heat. So this right here is sort of way. Now there's types of degree. This is a load right here. So this is the rest of your circuit. And as it goes, so it comes up, it uses a way of stepping down. But it's so fast that it's literally so fast that it literally looks like a straight line. It looks like a DC line. Okay. So use a buck converter. You could buy it on Amazon. They're like, you can get 3 for like $12. Go punch it into the search bar. Buck converters, they were really great, okay? So instead of using the 3.3 volts on your Arduino or Raspberry Pi, use those instead. Those will guarantee that your circuit is getting enough power. Okay? Okay, so that is pretty much that pretty much tells you about the buck converter and all that. Now let's talk about, sometimes what you have to do is you have to develop a converters. These converters, these are 3.3 volts to 5 volts. And what this does, it's the same. You gotta, let me draw a box right here. This is the 5 volt line. This is the 3.3 volts coming in. This is 5 volts coming in. Okay. Okay. 3.3 volts coming in. Okay. Coming in. Okay. And this is signal 1, signal 2, signal 3, signal 4, and this is, I'm going to say out 4, out 3, out 2, okay, out 1, okay, 5 volts coming in. What this does is your signals, your chips require 5 volts no matter what, even the incoming signals. It's like, I want 5 volts. Not only are you getting power from the buck right here, from the buck right here, this is the buck. This is also a buck. Remember I explained that. That's the stuff that you get. You know, it has that little, what that does is now you're getting enough power coming right here. Power. You're getting enough power right here. Signals are coming in. Boom, they're coming in. They're coming in like this into a square wave. They come out as a 5 volt wave. Very important stuff. Very important. There's a troubleshooting section where there's some cheap parts out there. You get like 5 of these for like $6. I highly recommend you buy the soldering part. I had some issues with soldering this stuff on. Soldering is got to be careful because soldering and heat and an IC. We'll discuss that on the troubleshooting section, not in this video. It's going to be, I think it might be on the next video. So that will explain that. So you have and so that explains it. So here's the explain is, yes, your little computer-looking machine, whatever it is, it's a Arduino Pi embed. I think there's even FPGA or something like that. It kind of does the same thing, but a different language. Yes, it's a smart thing. It's a smart, and it's now it's getting a lot of traction. We're getting some traction. You still need the blasters to help out. It's you still need those, so it's still going to require more space, because if it doesn't have enough power, your circuit won't work. Okay, let's go on the next one. Let's go on the next one. Why I used a capacitor, and this is kind of interesting. Oh, I'm trying to go as fast as I can, folks. Hang in there. I know. Hang in there. I know we got stuff to do. I know. Everybody's in a hurry. So this is a filtering circuit. I think that's kind of, a little bit of philosophical in there, So your 12-volt batteries right here, say it's 12 volts, comes in. There is this is plus, that's minus, and then it goes to the rest of the circuit. C-U-I-T, circuit. Okay, and that's going off the ground. Assuming that. So that's the rest. That's the big black box, but it doesn't matter. That's about. But then you have this 220 UF cap. Why? What's that for? Why the hell do I need that for? What's that for? What's that for? Does anybody know? Okay, now we're going to talk about these little devices. This is a device I got on Amazon. See, it's at 4.9. This is a converter. These are adjustable. So there's a little trim pot right here, and you can adjust going back and forth to whatever you want. You don't have to buy just a 5. You could buy whatever. This can go down to 3.3. You guys get the point. 3.3. Okay, and then you can go all the way up to 12. Now, I'm not quite sure if this is a boost. Let's see. Sometimes it is. I think this is only $1. 12, 10. Let's see if it is. Oh, see if it is. Does it go higher? Nope, that's as high as it goes. This is $1 only, which is actually, that is A-OK. Bucks tend to work a little bit better than boost. At least I think so. Okay, now let's go ahead and go on to the next section here. Let me pull my camera. Okay, my camera right here, this fancy dancy camera that I got. All right, now see if we can see. That's the oscilloscope, and let's see if we can focus on that a little bit further, folks. Let's see if I'm trying to use this darn thing. Did that work? Okay. Let me just, you can kind of see the waveform. Okay, so what that is this is my converter right here. Okay, that's my converter. And that's basically, there's an input of 3.3 volts and 4.8, close to 5 volts. And that shows the difference. Okay. All right, so hope you guys enjoy that. I think you guys can see it. Hope you guys enjoy. Please make a comment. Please subscribe. Comment, subscribe, and put a thumbs up. I like thumbs up. Don't put a thumbs down. No, if you put a thumbs down, I don't care. And I'll see you on the next Engineering Bart Show.